The idea when solving linear equations is to gradually unravel the equation to end up with x equals at the end. So in the first example, we have 3x plus 2 equals 23. If we begin by taking 2 from both sides, the plus 2 here will be cancelled out. So we're left with a 3x, and we've taken 2 from both sides, so we're left with a 21. So 3 times x equals 21. Then to get x equals, we must divide by 3. So x will equal 21 divided by 3, which equals 7. So 7 is the solution to the equation. 3 times 7 is 21, plus 2 equals 23. So in the second example, 11x plus 38 equals 35. So we want x by itself. We begin by taking away the 38, that's on the left hand side. So if I take away 38, I'm left with the 11x on the left hand side, but 35 take away 38 is actually minus 3. We are allowed negative solutions. And then I divide by 11 to find x, so x equals minus 3 divided by 11. It is a negative fraction. In the first example, I got a whole number. In the second example, I got a fraction. So, in the third example, 7x take away 1 equals 28. There's a minus 1 there, so I need to add 1 to both sides. So the left hand side is left with 7x, but on the right hand side I get a 29. I've added 1 to both sides, and then divide by the 7. So x equals 29 divided by 7, a top heavy fraction, which you could, if you wanted, write as a mixed number. There are 4 7s in 29, remainder 1, 4 and 1 7th. The fourth example has a negative coefficient of x, and there's a trick to this type of question. If I begin by adding 3x to both sides, the minus 3x here cancels out, so I'm left with 5 equals 11 plus 3x. I can then rewrite this as 11 plus 3x equals 5. And then remove the 11 by taking 11. So 3x equals 5 take away 11, which is minus 6. I then divide by 3. So x equals minus 6 divided by 3, which is actually minus 2. So when we solve linear equations, we can get whole answers, fractions, which are negative, mixed numbers, and negative integers. The trick is to use inverse functions to gradually unravel the equation. This video talks through how to solve equations where there are x terms on both sides. Now the method here is to get all the x terms onto one side, normally the left. So there's a 2x on the right hand side here. So if I take away 2x from both sides, that there will cancel out. So I'm left with 3x plus 3 equals 11. So that 2x is cancelled out, and 5x take away 2x is 3x. I now remove the 3 here by taking it away. So 3x equals 11 take away 3, which is 8. I then divide by the 3 here, the coefficient. So x equals 8 over 3, a fraction. Now, sometimes you find that there are more x's on the right-hand side than the left-hand side. And one simple method here is to rewrite the equation, swapping the two sides around, and then solve it in the same way. So there's a plus 3x there, so I begin by taking 3x away. So this becomes 5x, this cancels off, so I'm left with a 4 on the right hand side. I now need to add 11, so 5x equals 4 plus 11 is 15. And then divide by 5, so x equals 15 divided by 5, which equals 3. So again, when you find there are more x's on the right hand side, it often helps to rewrite the equation with the two sides swapped around. So in the third example, there are more x's on the left hand side, I'm okay there, but there's a minus 4x there. So I need to add 4x to cancel it off. So this becomes 9x, and the right hand side now becomes a 7. There's then a minus 2 there, so I must add 2. So 9x equals 7 plus 2, 9. And then finish by dividing by 9. So x equals 9 over 9, which equals 1. The general rule when we have equations with brackets is to nearly always expand the bracket first, though there are the occasional exception. But in these ones we'll expand the brackets first. So 5 bracket x plus 2 just means times the bracket by 5. So 5 times x is 5x, and 5 times 2 is 10. And this just equals 11. We then use our normal equation solving techniques to get x equals. So I first of all take away that 10 to cancel it out. So 5x will equal 11 take away 10, which is 1. And then divide by 5. So x will equal 1 divided by 5, or 1/5, a fraction. The second one, bracket again, so we expand the bracket. I times both things by 3. So 3 times 2x is 6x. 3 times 5 is 15. There's a minus there, so it's minus 15. And that just equals 7. I then must add the 15 to cancel the minus 15. So 6x will equal 7 plus 15, which is 22. I then divide by the 6. So x will equal 22 over 6, which cancels down to 11 over 3. So the rule is to expand the bracket first. And this rule still applies in the third example. We don't do 3 plus 2. The 3 is not times in the bracket, only the 2 is. So I begin by expanding the bracket. 2 times 3x is 6x, and 2 times 4 is 8. That's the bracket part worked out. There's also a 3 there, so it's 3 plus this bracket part, and that equals 8. The next step is to simplify. A 3 plus an 8 is 11. So 11 plus 6x equals 8. And we then solve the equation as normal. There's an 11 there, so I take away 11. And I'm left with 6x equals 8. Take 11, which is minus 3. Then I need x equals, so I divide by 6. So x equals minus 3 over 6, which is the same as minus 1 half. So the golden rule is always expand the bracket first. And if necessary, you can then simplify before solving. Cross-multiplying is a technique for solving equations where there are two fractions on either side of the equal sign. Now, it's quite a simple technique. It simply says that we times the other numerator by the other denominator. So I times that side by 2, and I times this side by 3. Now, it helps if I place a bracket around the entire numerator. If I times this one by 3, I get 9x, take away 12, and I've times that one by 2, so that equals 10. And then I add across the 12, so 9x equals 22. So to finish off with, I divide by 9, so x will equal 22 over 9. So, again, I'll place brackets in first this time. It's a pretty good technique to use. And then times the numerators by the other denominator. So I times up by the 7 and up by the 3. So 7 times this bracket here. 7 times 5 is 35. 7 times 4 is 28. So it's 35. X, take away 28. And then this here has been times by 3. So 6x plus 3. And then want the x's on the left-hand side in this case, so I'll take away 6x. So that leaves me with 29x. Take 28 equals 3. And then add across the 28. So 29x equals 31. And then divide by 29. So x will equal 31 over 29. Now this technique still works even with more complex looking equations. So I'll place the brackets around the multiple terms first. And the rule still applies. I times the opposite numerator by the other denominator. So I times up by 5 and up by that entire bracket. So it's 5 lots of this bracket here. So it's 25x, 5 times 5x, and 5 times minus 2 is minus 10. And that equals 2 lots of this entire bracket. Well, 2 times 3x is 6x, and 2 times minus 1 is minus 2. And then we solve the equation using our normal techniques. So I'll take away 6x first, leaving it as a minus 2, being very careful there. And then add 10, so 19x equals minus 2 plus 10, which is 8, and then divide by 19, x will equal 8 over 19. The golden rule, always times up by the denominator to the other numerator, putting brackets around the tops where necessary, or the bottoms where necessary. And remember to times both things in the bracket by the required number. When you have an equation with quite a simple fraction in, the method is to multiply up by the denominator. So if I times up by 3, then I end up with 5x equals 2 lots of 3. So 5x equals 6. So I times up by the denominator, and then I finish off by dividing by the coefficient of x. So x in this case equals 6 over 5, or 6/5. Now occasionally we have a number as well as a fraction, so in this case a -1. We can use our normal equation solving technique, so if I begin by adding 1, then 7x over 4, I've added 1, so it will equal 4 plus 1, which equals 5. We're now back to the same style of equation, so I can times up by the 4, so I'm left with 7x equals 5 times 4 equals 20. I then finish off by dividing by the coefficient of x, which is 7, so x equals 20 over 7. Now this technique still works even when the x is in the denominator part of the fraction. So here I times by 3, here I times by 4. In this one I times up by the entire 2x. So I end up with 5 equals, and 7 times 2x is 14x. If I so wish, I can now rewrite this as 14x equals 5. So 14x equals 5, divide by 14, therefore x equals 5 over 14. The exam questions often require you to apply algebra within a shape and space example, often triangles. They always say not to scale, so you can't measure to find x using a protractor. Anyway, we know that in a triangle the angles always add to make 180. So this plus this plus this must equal 180. So we can begin by writing that down mathematically. 3x plus 2x plus x minus 40. They're the three angles. They must equal 180 due to the degrees in a triangle, making 180. I can then simplify. 3x, 2x and 1x is 6x. So 6x take 40 must equal 180. I then solve like any normal equation. I have to add 40. So 6x must equal 220. I then divide by 6. So x must equal 220 over 6, which is the same as 110 over 3. And of course, when we know x, we can find each of the angles. E.g., this angle here is 3 times x, this angle here is 2 times x, and this is x take away 40. In the second example, we have two parallel lines, hence the arrows. Now when you have two parallel lines, the angles contained therein add to make 180. So 5x plus 100 minus x must equal 180. This can be made simpler. 5x take away x is 4x. So 4x plus 100 must equal 180. I therefore take 100. So 4x equals 80. And then divide by 4. So x is equal to 20. So this angle, 5 times 20 is 100. This one, 100, take away 20 is 80. Now it's normally good practice in the exam to explain your logic a bit more carefully. So this fact here about 180 can be referred to as supplementary angles, and often you'll put in brackets the reason for that. just as in the first example, you may put triangle equals 180 degrees, and that extra step is often required to get the full marks in the exam. Now, just a quick comment. Those of you who are eagle-eyed would have recognised that this answer here is actually less than 40, which produces a negative angle here in the triangle. This was just an example made up on the spot to explain the technique. In the exam, of course, you'd get valid angles within the actual triangle itself.